So, in the last lecture we just started discussing on mixed potential theory, and this lecture is lecture number 38. And here we will continue kinetics of corrosion. And now our discussion mode would be mixed potential theory. In fact, in the last lecture, if we see that we have put forward two hypotheses, and those two hypotheses are basically any electrochemical reactions. This is first hypothesis, can be divided into two or more partial oxidation or reduction reactions. And the second hypothesis says that because of this process, that means more partial oxidation and one or two or more partial oxidation and reduction reactions, the electrode will achieve a mixed potential which is attained due to these partial reactions definitely, and there should be no net accumulation of charges, and this no net accumulation of charge would basically indicate the laws of conservation of charge, and that time IA should be equal to IC, and that IA equal to IC means there is, for example, a metal when it is electrically isolated, and then there should be no current flow. In fact, if I try to look at this particular example where zinc is immersed in HCl, so actually there is no net current flow in the zinc, rather when this mixed potential is achieved, IA equal to IC, and that also indicates I corrosion, because at this rate the corrosion will take place, and that also corresponds to a mixed potential which is also called E core, since zinc is acting as that electrode, and on top you have cathodic as well as anodic reaction, zinc minus 2E equal to zinc plus plus and H plus 2E equal to H2. So, this leads to one redox reaction which is zinc plus 2H plus zinc equal to zinc plus 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 H2. So, and this electrode would achieve unique mixed potential which is not same as the potential for zinc plus plus, that is single redox reaction, this half cell reaction, they would also have their reversible potential to begin with, and this potential is not the same as that particular begin with the potential where from it has began to shift from that potential to this E core due to this combined reactions. So, now we see that the concept of I core and E core. Now, let us try to understand this mixed potential theory and kinetic reaction, kinetic equations rather, in the form of and Imax. These two equations, if we combine them, we would see that it leads to modern electrode kinetics theory, kinetics effects rather, electrode kinetics theory or effect. So, it would lead to modern electrode kinetics theory. So, this combination of these two. Now, to begin with, when we have this situation, let us say that for zinc it would have a potential E0 which is minus 0.76 volt, and at that time I have zinc plus 2E equal to zinc. For this reduction reaction is actually happening in the standard state, Let us assume that in the beginning it has zinc ions, and then we have this potential to achieve, which is the equilibrium potential. So, at that potential I have I 0, which is exchange current density. Of course, it is on zinc surface, and zinc plus zinc has got some value. It's, let us say its value is around 10 to the power minus 7 ampere per centimeter square to begin with. Now, similarly, if I consider hydrogen electrode which is forming on zinc surface. So, hydrogen electrode, the standard hydrogen electrode what we have seen before, it is basically platinum electrode or platina electrode is used, but on zinc surface we can also constitute an hydrogen electrode, and that time I have E 0 to be 0 volt and I 0 of hydrogen exchange current density, which is actually on the zinc surface, would be, let us say, some value around 10 to the power minus 11 ampere per centimeter square. If I try to plot them on log I versus potential axis, let us say this is my zinc potential, which is 0.76 minus volt, which is equivalent to E 0, and this is my E 0 for volt for hydrogen. Now, exchange current density of hydrogen on zinc surface, I 0 zinc H 2, and exchange current density on zinc surface for zinc reaction. So, this is I 0 zinc, I simply put zinc without putting that zinc plus slash zinc, because it is taking little bit of space. This is the situation in the beginning to begin with. So, here it indicates H 2, this is non-corroding reversible situation at this point. Here also this is zinc plus 2E equal to zinc, this is non-corroding and reversible condition. And this was the potential in the beginning for both these half cell reactions, because we have to consider these two half cell reactions. This is oxidation and this is reduction. These are basically two half cell reactions, and to begin with we have assumed that they are starting from the standard potential. Now, for both the cases, for hydrogen and zinc, let us say, let us draw that this is for hydrogen, this is for zinc. If I try to see over voltage as a function of log I, this is, let us say, 0, over voltage equal to 0, which is actually indicating E 0 to be 0 volt, and here neta equal to 0, this is indicating 0, which is actually indicating E 0 for E 0 equal to minus 0.76 volt for zinc. They would have their own cathodic and anodic polarization plot. And let us say that we are in the activation polarization regime, that means in the low current region, because concentration polarization starts at a very high current density. So, if I consider the activation polarization for hydrogen reactions, it also has its own cathodic and anodic reactions. So, this is cathodic part, anodic part for hydrogen. So, this is 2 hydrogen equal to 2 H plus 2 E, and this is cathodic part H 2, and in case of zinc, this is anodic part, which is zinc minus 2 E equal to zinc, and this is cathodic part zinc plus 2 E equal to zinc. So, they have their own cathodic as well as anodic Tafel plots. I would say that this equation neta equal to beta log I by I0. According to these equations, they have their own plots. But since their potential is far off, one is at 0 and another one is minus 0.76. As per this mixed potential theory, if I look at that mixed potential theory, it says that the mixed potential of electrode will be achieved due to partial reactions. Now, there are two different potentials, so they must achieve some potential which is in between these two potential, and that is unique for this particular situation. How can they achieve? That can only be achieved, for example, if it goes anodic side and if it goes cathodic side, they cannot achieve a single unique potential because their potentials are basically moving away from each other. So, the only way they can achieve a mixed potential by moving this one on the anodic side and this one on the cathodic, then only they can reach unique potential. And when they would like to do that, so that means they would follow their own anodic polarization plot and cathodic polarization plot as per these equations. So, in this case, in case of zinc case, this polarization would follow according to this line, and here the polarization of hydrogen reaction would follow this line. So, now they will meet somewhere here. Once they meet somewhere here, you see that the potential is E chord which is in between this and this, and for that you could see that polarization for zinc is on the positive side and the polarization for hydrogen is on the negative side. So, hydrogen is cathodically polarized and zinc is anodically polarized in order to achieve this mixed potential. Now, interesting thing, the second postulate or the second hypothesis is also met here. If you see this, it says that when it reaches that mixed potential, there is no net accumulation of charges. So, that means the current density for cathodic reaction which actually accepts electron, and then current density for anodic reaction which actually leaves electron, these two equations, these two rates are same. So, that means the rate at which electrons are consumed due to cathodic reaction, which is hydrogen evolution reaction, is same as the rate at which electrons are generated by the zinc dissolution, which is anodic or corrosion reaction, and they are meeting at this E chord point. This is this point, E chord point, and corresponding current density should be I chord, which is nothing but I A equal to I C. And whenever we have this situation, there is whatever electrons are generated are basically consumed. So, there is no net accumulation of charges for this electrically isolated zinc piece in HCl medium. So, if I try to plot here, so it would be so this is E chord and this is I chord. This is the crux of mixed potential theory. So, this potential is called mixed potential, and the system would like to stay here, and the corrosion of zinc would take place as per the rate decided by this I chord. Now, how do I get this I chord and E chord experimentally? Now, whenever this zinc block is immersed in HCl medium, after some time it will try to achieve this, because these rates are going at a different, this I chord and this IA as well as IC, they are actually taking time, because finally it has to reach to this constant rate, and then there will be no net current flow in the system. So, the system, this zinc would remain at this potential. So, if I try to measure this potential of zinc without sending any current through that particular zinc plate by a standard hydrogen electrode, so that means if we have this zinc HCl medium and then I connect it to hydrogen, standard hydrogen electrode, and I connect a wire with this zinc, and then if I try to measure the potential, it gives me potential. After achieving this potential we call it without sending current. Remember, without sending current we are not connecting that circuit. So, that time we see that the potential is termed as OCP, open circuit potential. Remember, once we try to measure this zinc potential with a standard hydrogen electrode, then initially that potential is actually switching from one potential to another until unless it reaches to this potential. So, once we allow little bit of time, we see that the potential is actually potential has achieved this particular E core or OCP, and it is maintaining at that potential with time. See, this open circuit potential is the new point from where we have to consider the polarization during experimentation, and that is what in the lab we do polarization experiment, and that time we try to achieve this open circuit potential, which is the stable open circuit potential, and then that one would be considered as a 0 over voltage, the new 0 over voltage, and then we try to go positive or negative side and then try to see that what is my net current flow or I applied. In case of single electrode system, we have seen that the actually in case of single electrode system what we have done. So, this is neta equal to 0, this is I 0, these are the two sides, and then we saw that if I send applied current, that means when the rate of cathodic and anodic reactions are different, then the plot would look like this. So, this is my I 0, and when I 0 is achieved, there is no net current flow in the system. Similar way, here it is M n plus equal plus N E equal to M, as well as this forward as well as backward reactions. This is the non corroding situation or single electrode case. But here we have two different reactions, it is not single electrode reaction. One reaction is zinc dissolution, another one is hydrogen evolution, and this point would be the new set point, the way we have considered neta equal to 0 for single electrode case. Now, then if I try to do the same experiment, we will get a curve like this, and then the linear portion we have to consider, this linear portion, and the linear portion we have to extend, and then finally we will achieve to this point, and this linear portion is achieved the way we have done for this case. It is the same way. In this case we have to consider I C minus I A, and this is for hydrogen and this is for zinc, and in this case also we have to consider the difference between I A minus I C, and this is for zinc and this is for hydrogen. So, that is what we get this Tafel plots, and accordingly we can extend this linear portion and these two linear portion backward, and we can achieve this particular point, and that is basically nothing but I core and E core. This is one important information what we achieve, what we get by doing Tafel experimentation. So, this particular part will come in the corrosion part 2, but still when we have considered this we are just explaining little bit. So, if I try to look at the mixed potential theory in nutshell, we could see that the new potential is achieved, and that new potential is when it is achieved due to the polarization of those partial reactions. One definitely would be cathodic and another one is definitely anodic polarization in this simple situation where the entire reaction is divided into two parts. One is one single cathodic reaction, another one is one single anodic reaction. Then once we reach to that mixed potential, at that mixed potential I could see that if it is isolated metal block in that particular solution, there is no net current flow, and that can achieve if I could see that IA equal to IC at this point. That is what we have understood in this particular diagrams. In addition to this, remember this is an open system. If it is an open system, so since this is open system, the hydrogen bubbles are forming and they are actually going out. Now, if we have it in a closed system, definitely this reaction would arrive at equilibrium. This reaction will arrive at equilibrium. That time also it will be E core and I 0, which is equal, not I 0 is basically I core, the same point will be achieved. But if it is an open system, if we do not change the temperature, then hydrogen will keep on going out and then this reaction will go forward. So, the zinc will keep on corroding. So, that time it will not be equilibrium situation, it will be non-equilibrium spontaneous situation since hydrogen is going out. So, now let us consider some of those effects of mixed potential theory, some of those consideration of kinetic factors. So, one such kinetic factors is definitely I 0. Now, I 0 for let us say hydrogen evolution reaction on different metal surfaces are different. For example, on platinum surface, as we have seen, its value is around 10 to the power minus 2 to 10 to the minus 3 ampere per centimeter square. For gold, it is around 10 to the power minus 4 to 10 to the minus 5 ampere per centimeter square. And for zinc, for this hydrogen evolution reactions, remember this I 0 value, I am just putting this I 0 value, it is around 10 to the minus 11 ampere per centimeter square. All these values would have definite effect on the zinc corrosion rate. Now, how we are considering? For example, if we have a particular beaker, let us say 2 beaker, one beaker we have a zinc plate, zinc block, and the concentration of both the electrolytes, that is acid medium HCl, is same, and another case I have a zinc in connection with a platinum plate. This is let us say platinum plate and this is zinc. Now, we would see that in this case we would have very high rate of corrosion of zinc. Why? This can be explained by using mixed potential theory. So, when we try to see these two situations, we have to first look at the diagram, which the diagram what we have shown here, these diagrams are called Evans diagram. So, these Evans diagram are basically not considering the practical diagram, which is I applied versus potential or potential versus I applied. This is basically potential versus log I as per this polarization or the Tafel equation. We will not consider there this what happens if we go on positive side or negative side and what would be the variation of I applied. So, that case we have to again consider this. For zinc, this is E0 zinc and this is I0 zinc on zinc surface, and then we have E0 for hydrogen, which is 0, this is minus 0.76 volt, and then we could see that this is my I0 of hydrogen reaction on zinc surface, and accordingly we are achieving the mixed potential theory. As per the theory, this is the potential what we would achieve. This is the mixed potential, which is E core, and this is I core, isn't it? So, that is what we have seen. Of course, it will have its own anodic over voltage also, but since as per the discussion what we have seen that it will go to negative side and this will go to positive side, isn't it? Now, if we have another reaction, this in this case, this is the situation, this diagram, this Evans diagram is indicating this situation. Now, in this situation, it will be a little complicated, and if I have understood this mixed potential theory, it can be analyzed very easily. But we will take it up in our next lecture, and let us stop here. Thank you very much, and wait for the next lecture, where we will talk about this effect of increase in exchange current density for a particular cathodic reaction by changing the metal surface, and then its effect on corrosion of metal. Let us stop it.